In this video, we'll introduce a set of logical properties that are of central importance to the study of sentential logic. Then we'll focus on the specific property of logical equivalence and on the way of determining it with truth tables. There's a small group of properties that are of great importance to logicians, and each of those properties applies to a different kind of entity. Each of them could be the focus of our study of logic, and in fact, different logical tools and methods can take one of these properties as its point of departure. In the end, however, each of these properties is definable in terms of the others, which means that all the techniques that we'll study, regardless of their focus, will end up being equivalent. We'll have plenty of time to discuss each of these properties in future lessons, but for now, let's just mention them. If we focus on arguments, that is, sets of statements that contain premises and conclusions, we'll be interested in the property of validity. Validity and invalidity are features of arguments, then. If we focus on sets of statements, regardless of the number of statements in the set, and without dividing them into premises and conclusions, we'll be concerned with the property of consistency. If we consider pairs of statements, we'll be interested on whether they are equivalent or not. Last, if we look at individual statements, we will determine whether they are logical truths, contradictions, or contingent statements. As I said earlier, we'll devote considerable time to the discussion of each of these properties, but today's video will deal with equivalence. Two sentences are equivalent if they are true in exactly the same situations. We can test for equivalence with the aid of truth tables. Suppose that we have two sentences, X and Y, and that we make a truth table for each of them. Well, if X is true in every row in which Y is true, and vice versa, this means that they are equivalent, as far as SL is concerned. So we can say that in a truth table, a pair of sentences is logically equivalent if and only if there is no row in which the members of the pair differ in truth value. If the sentences are not equivalent, then they are, unsurprisingly, inequivalent. Inequivalent sentences can differ in truth value. There are situations in which one is true while the other is false. So we can say that a pair of sentences is logically inequivalent if there is at least one row in which the members of the pair differ in truth value. These definitions determine a method for showing equivalence and inequivalence between sentences. First, we make a truth table for the atomic sentences contained in the sentences we are comparing. Second, we place each of the sentences we are comparing in a separate column. Third, we calculate the truth values for all the rows in each of the columns. Fourth, and this is the new step, we compare the two columns. If there is at least one row in which one of the sentences gets a T while the other gets an F, then they are inequivalent. Otherwise, they are equivalent. Here's an example. Consider sentences 1 and 2. Intuitively, we can see that they are true in exactly the same situations, but we can decisively show that they are equivalent by using a truth table, like this. Both sentences contain A and B as their atomic sentences, so we start our truth table with a column for each of these sentences. We know that we want to compare not A or B and not A and not B, so we'll put each of these in a column. However, each of these sentences is itself composed of complex sentences, so we need to devote a column for each of the components. Sentence 1 is not, open parenthesis, A or B, close parenthesis. We can see that it contains A or B, so we can start by making a column for it. Then, to fill the column for not A or B, we simply flip the values in the column we just built. Now let's work towards the other member of the pair. Not A and sentence not B are the components, so we devote one column for each. As always happens with negation, we simply invert the values of the column we are negating. Once we have these two columns, we fill in the values for our last column simply by applying the valuation rule for conjunction, and we write T if both columns are T and F otherwise. Okay, now that we have our two columns, one for each of the sentences we are comparing, we proceed to the equivalence test. Let's go row by row. Is there any row in which they differ? Well, in this case, no. They have exactly the same value at every row. This shows that both sentences are true or false in exactly the same situations. Therefore, they are equivalent. Now consider these two sentences. For this pair, I've already filled the first two columns. Now let's proceed to fill the last two columns, each of which corresponds to the sentences we are comparing. We can see that they do differ. In rows 2 and 3, one of them gets a T, while the other gets an F. That means that there are situations in which they end up with different values. Thus, they are not equivalent. Now, let's do an exercise to test our knowledge. For each of these pairs of sentences, indicate whether they are equivalent or inequivalent. Again, pause the video and take your time. Are you ready? Okay. The sentences in the first pair are not equivalent. If you make A false and B true, look at the third row, the first comes out false with the second true. Those in the second pair are equivalent. You can see that they get the same value at every row. The same happens with the third pair and with the fourth one. Last, the fifth pair does not contain equivalent sentences, since, as you can see, rows 2 and 3 get different truth values. Okay, this is all for this video. See you in the next one.